Hi, this is Terry Kuzma here at Penn State University. We're exploring bottom-up manufacturing, and one material we're going to take a look at today is carbon allotropes and the processes and applications. This will be a multi-part series, so there's a multitude of different carbon configurations that we can engineer using carbon as a base material. So we're going to take a look at the most popular modes of operation with this particular material. So what we know, carbon comes from the Latin word carbonium, meaning charcoal. Well-known forms of carbon include diamond, coal, and graphite. Naturally, these items are made of carbon exclusively, but they offer different functionality depending on how they're arranged. Carbon likes to bond to carbon and many other elements. Individual carbon atoms can covalently bond to other carbon atoms. Covalent bonds and the molecules provide superb stability and resistance to stress. By careful processing, the carbon can be shaped into rods, tubes, balls, and sheets. Unique materials from one inexpensive material offers a wide variety of applications, and that's why we would like to learn quite a bit about carbon and certainly apply it like nature does. So this is a chart, the periodic table here, and it tells us all of well, not all, but some of the derivatives that we can get from carbon. So if we look at the basic periodic table, we can see that we get a carbon silicon derivative, carbon germanium. So we can get different types of material, and you can see that a lot of these materials are tremendously common, like the CF group, CO, etc., CH. So these things are ubiquitous in our local environment. So these have the core chemistry down here is organic, shown in the blue. Academic research and no widespread use is the stuff that's shown in this yellowish color. And then the ones that are very handy to us are the ones in green. So these are the common ones that we use quite a bit in everyday life. So carbon itself is the fourth most abundant chemical element in the universe, and it's the other ones that lead that are hydrogen, helium, and oxygen. Carbon has the ability to form very large chains of interconnecting carbon-carbon bonds. There are more known carbon-containing compounds than all the compounds of other chemical elements combined, except those of hydrogen. So it's super duper popular and super duper useful. The carbon has 4 valence electrons, and these are available to make covalent bonds. Each of these electrons can pair with an electron from another atom to form a strong covalent bond, making materials like graphene very, very strong. So this is a look at the different types of bonds that we would have in carbon. So the first shows us a single bond in carbon, and this is a typical configuration. And then what we get is, and if we look at the middle, we can see the double bond in carbon, and then on the right is the triple bond in carbon. And these make the material very, very strong. So each one of these electrons can pair with an electron from another atom to form a strong covalent bond. And again, this makes things like graphene, like this sheet over here, very, very strong. So carbon can be the basis for an entire range of intrinsic nanometer scaled structures. So we typically have materials like the fullerene, which is a zero-dimensional structure. We have nanotubes, which have one dimension or one-dimensional described as nanoparticle. It'll have one dimension that's greater than a nanometer. And then we can have a graphite, which has 2 dimensions greater than a nanometer, but it's a nanometer thick. And then fullerene solids, there's all kind of different types of fullerene configurations, such as the C70, C76, C78, and C80, and also higher order variations, and materials that have both multitude of configurations within them. So we're going to take a look at these in detail throughout the presentation. So these are some selected allotropes of carbon, and an allotrope is basically a functional material, a functional system made out of the same type of material. So again, carbon is the basis for these, but when we assemble carbon in a particular mode, we get a different operational system. So there could be, as we see, an A, diamond, graphite, and down the list. And again, we're going to review these throughout the presentation. So what we can say is, and a term that's used quite a bit is the synthetic carbon allotropes, and we refer to them as SCA. They're carefully crafted and be manufactured as one topology, confined objects in 0, 1, and 2 dimensions as previously shown. So what we're going to do is we're going to take a look at the different common carbon allotropes throughout history. So we're going to start here on the left, and we're going to look at diamond-like coatings. We're going to review details in there, and then we're going to move on to buckyballs, then to multi-wall carbon tubes, etc. So we're going to move to the right in here historically. So that's how I divided up the topics. So here's how we're going to examine unique materials throughout this presentation. We're going to look at the original discovery, or the one that's the most popular. These things have been discovered multiple times, but we'll look at the people who've gotten the most credit for the initial discovery or the practical use of the material. And then we'll look at the material property and physics. Then we'll look at manufacturing methods, and then some applications for that particular material. So in the history line here, what we're going to look at first is diamond-like coatings. So we'll look at the discovery, etc. So in 1953, this gentleman discovered how to deposit diamond-like films in a gas discharge plasma, and then it moved on from there in the history of this particular material, and certainly an important material. So in the mid-70s, diamond-like coatings first made from hydrocarbon sources in the glass glow discharge. And then in 1985, diamond-like coatings were starting to be used for diamond-like recording material. And then in the 2000s, we can see a rapid growth in articles around this topic, focusing on the application of diamond-like coatings. So let's take a look at the physical properties. Diamond and diamond-like films, each carbon atom in diamond is covalently bonded to 4 other carbons in a tetrahedron. These tetrahedrons together form a 3-dimensional network of a 6-membered carbon rings, similar to cyclohexane. This stable network of covalent bonds is in hexagonal rings is the reason why diamond is so strong. So this is a look at a 3-dimensional structure view of the diamond cubic structure. So we can see these things manipulated 3-dimensionally, so we can take a look at their bonds and how they're available to bond within the system. So diamond itself is certainly one of the most well-known allotropes of carbon. It is the hardest known natural mineral that we have on the planet. Industrial diamonds are valued mostly for their hardness and heat conductivity, and diamonds are embedded in material or in systems such as drill bits and saw blades, or ground into a powder and used for grinding and polishing and chemical mechanical planarization. So certainly they're used here in the left aesthetically, I guess, for jewelry, but by the millions of tons where they use or by the tons, I should say, they use these materials on saw blades, etc. So I know in manufacturing of things like automobile engines, etc., the most costly contribution is cutting tools. So this will keep the cutting tool sharp, and so that you don't have to replace the cutting tools as often. So there's millions of 400 million carats of synthetically diamonds are produced annually for industrial use. So this is the equivalent of 80 tons, and this dwarfs the natural mining of natural diamonds. So 4 times as much is produced by man-made synthetically than is mined. So diamonds are often used as heat sinks in electronics because diamond has a high heat conductivity. And then diamond coatings are also very, very popular on optical lenses to prevent abrasion. So if you were to go buy some expensive Nikon lens, etc., or a Leupold scope, you wouldn't want to clean them the first time and then get scratches on the lens, and then you get aberrations in your optics. So what they would do is a final coating, put these diamond-like coatings on the lenses to keep the lenses from scratching. So again, these are the physical properties that we looked at, and this is an sp3 orbital with a bonding of 109.5 degrees. So this provides this material structure provides both hardness and low friction under sliding conditions. and these molecules are responsible for high Young's modulus, hardness, and diamond-like quality. So this shows us the different diamond-like material properties and the mixtures that we would consider in the diamond-like films. So we can have ranging up here from the sp3 orbital, which is diamond-like. These are other materials which are similar from other deposition techniques. And then we'll look briefly at manufacturing methods. There's a tremendous amount of manufacturing methods for diamond-like materials, but we'll take a brief look at some. So these are RF plasma, and this shows the energy of the deposited carbon species in electron volts. So we also have ion beam deposition, we have vacuum arc deposition, magnetron sputtering, and then pulsed laser deposition. So this shows us schematic drawing of the pulse laser beam deposition. So basically what we're going to do here is focus our high energy laser on a graphite target while we're rotating the target, and that rotation along with the beam energy is going to control the size of the atoms that are released from the graphite target. And then what we're going to do is apply a bias to our substrate. And again, to get uniformity, what we're going to do is rotate that substrate system, the cathode. We're going to rotate that so that we get uniform deposition on the surface. So this is a typical pulse laser deposition tool used for diamond-like films. And this could be used quite a bit for materials like I said before, optical lenses. So let's take a look at some applications. We already did, but we'll take a look at some more. So there could be protect structures from potentially destructive contact. The diamond-like films reduce the likelihood of hard particles penetrating into tools or parts. It can protect moving parts from abrasion, preserving smooth movement, and it offers a low coefficient of friction. So the reduction in friction reduces the need or the type of lubricant that we would use. And then this system tends to be chemically inert and highly resistive against oxidation and corrosion. So the material itself must be able to, that we deposit on, able to tolerate internal stress and resist delamination. That due to high film stresses, a lot of times these diamond-like carbons have poor adhesion to the parent material. This could be resolved by using multi-layer stacks that include an adhesive layer, and then layers that would be able to give some kind of a mechanical movement to the DLC material. These stacks are also reduce film stress, allowing thicker coatings, and then thicker coatings generate exceptional properties such as extremely high microhardness, low coefficient of friction, and slower rates of wear. So these are some examples of parts that have diamond-like film coatings on them. And so these are perfect for mold materials and automotive wear parts, again, to reduce friction and wear. They're often used on cutting tools to provide both lubrication in a dry environment so that the lubricant doesn't interfere with the machining process. And it's also used in biomaterials. For example, if we were to apply diamond-like coatings on a stainless steel screw that would be used to couple bones together, what that'll do is allow a reduction in stress on the bone by 50%. So that's important when the screw is inserted, and it's also important if we had to remove the screw. So it adds some intrinsic lubrication to the system. So we could also use the diamond-like film as a decorative aspect. So this shows us a watch that has this blackish coating on there. And I know that there are now like black synthetic diamonds that women use, I guess women primarily for jewelry. I know I bought my wife some black Labrador dog diamonds last year for Christmas, and she liked them quite a bit. They looked quite a bit like that. They had a nice sheen to them. So what this can do is we can apply this to other underlying coatings, and it gives a shiny and black appearance. And again, this won't allow this material to corrode, etc. So it's a pretty nice application. So right there, what I wanted to do is end this particular introduction to diamond-like coatings. And what we're going to do in part 2 is we're going to take a look at buckyballs. So I'd like to thank you for your attention, and we'll talk to you next time when we start our discussion in buckyballs. Take care.